Good evening, I am Mr. Ish. You are joining me for a useful and interesting video here. Derivative coefficients. You know at any time you have a coefficient for a derivative, you can push that coefficient out and complete the derivative and bring the coefficient back. We've presented something similar like this with regards to integrals, so it makes sense to talk about it with regards to derivatives. If you have something which looks like this, you do the derivative, you should get a result which looks like that. Whether you were perceiving it in this way or whether you were looking at it in this form, the end result should still be the same. C being unaffected and multiplying with the derivative of f. In both instances, the result is the same. In the first instance, C went with the derivation procedure. In the second instance, C was pushed out, then it came back and reattached with the derivative. And why is that the case? Very simply, and this proof doesn't have to be a formalized one by any means, you can do a very simple informal proof. Think of this situation like this. You're looking at something which looks like CF. You can view this as an f function and you can view this as a g function, and you can apply the product rule and you should see this process through. You would have the g function multiplied by the derivative of your f function plus, remember the product rule template, plus the f function multiplied by the derivative of the g function. The derivative of c, which is a constant, is always 0. It zeroes everything out. You end up seeing something which comes out like this because the derivative of f comes out as an f prime. It attaches with this and you have this. Likewise, you can also look at something like this. In this manner, you have c pushed outside. Then you just simply did the procedure with the derivative of f. You ran it through whatever function it was, its template, and then you brought c and you attached it here. And both of these instances, the outcome is the same. But let's look at it in a different light. We have a function f of x. Let it equal cf, a combination of a constant and a function. And the derivative of that function, well, you know where we're headed. You do the basic definition of a derivative. You're looking at this. Constant times f of x plus h minus constants times f of x, all divided by h. The basic definition of a derivative, you could isolate the constant. When let's do that, limit as h approaches 0, I isolated the constant because it was a common term. I had f of x plus h minus f of x all over h. When I isolated the constant, I could use a constant multiple rule of limits and push it outside, and my end result was this. C, limit as h approaches 0 at f of x plus h minus f of x over h, which the derivative of this is easy. The derivative of that is just that. And this here represents the derivative of the original function we were looking at, which was cf. And the derivative of that would be right here, c times the derivative of f of x. And you can see the result is still very similar to what you're seeing over here. In a very similar but slightly redundant manner, you could look at everything like this. If f of x is equal to cf, you can look at everything like this, where your derivative with respect to that x is equal to c multiplied by limit of h of 0. Here the c has been pushed out from the very beginning, and you're just looking at all of this remaining part undergoing the derivation procedure, which of course you know will lead you to that, and the outcome is still the same as you see over here. In all instances, when you have a function which has a constant, you can always push it outside and then reattach it, or you can send it through your derivative procedure and the outcome is the same. But in all instances, if you just push the derivative outside, you'll always be better off, because treating something as a constant and running it through a derivative procedure is unnecessary, especially when it will zero out. When you look at the derivative of that constant alone, it will zero out no matter what. So why even bring it through the derivative procedure when you can just push it out and bring it in at the end? The coefficients that you could very easily push outside prior to your derivation procedure, obviously we know that a numerical constant would very well fit this bill. It could be anything from a number. We can say a is a number. It could be a fraction, a rational expression. It could be an irrational number, you know that. Something like root 2 or pi. These would very well fall into the parts of a numerical constant. It could be a variable even. If a variable is not being addressed in terms of its derivative, it could be a single variable that you can push outside. It could be an expression even, or part of an expression that you push outside. Consider the formula for volume of a sphere 4 3 pi r cubed. If supposedly you were doing a derivation procedure involving only the radius, you could literally push 4 over 3 pi outside. You could do that. If you're looking at something like supposedly a certain formula is 1 over 3 pi r squared h, you're only looking at the derivative of the height component here. You know, this is the volume of a right circular cone. You could literally just push out the 1 over 3 pi r squared component, and the h is what would go through the derivative procedure. So you know, you can just push out parts of an expression, or you can push out an entire expression. So these are all the types of items that can be pushed outside, and then you do your derivative, and then you push them back in and attach them to the derivative. So keep all of this in mind, that you have this level of flexibility to push out and bring back, and your end result will still be the same. So let's end this video with that statement there. Thank you for watching. Stay tuned. Have a nice day. Bye.